Okay, when you look around today, I mean, you just can't help but be struck by it, right? The incredible pace of change. Computing, AI, it feels like it leaps forward almost daily. But that really brings up a big question for us. How is all this exponential progress actually happening? And, what's hidden underneath? What aren't we seeing?
That's exactly what we want to dig into in this deep dive. We're planning to unpack these sources you've given us, pull out the really key insights about, well, the past, the present, and maybe the future limits of AI and computing. Our aim is really to help you understand not just what's going on, but why it actually matters. And there's some pretty surprising facts in here, too.
All right, let's get into it. To really grasp this, we need to look back. I mean, this isn't totally new, right? We've seen amazing progress in computers for, well, decades now.
We have indeed. And a really crucial starting point, is Gordon Moore's observation. Back in 1965, we call it Moore's Law, but it's important to remember it wasn't like a law of physics or anything. It was more an observation that kind of became a target. He first said the number of components on chips would double each year, with costs staying low. Then in 75, they revised it specifically, the transistor count doubling every 2 years. And the key thing, the semiconductor industry basically took this on board as their roadmap. It drove everything.
That's a really interesting way to put it, a roadmap, not a law. Okay, but some people say that original idea, the density doubling, it's kind of hit a wall, functionally speaking.
Right.
So how do these newer things, like system-on-a-chip SoCs, how do they keep that spirit of exponential growth going? Or is it? Is it something fundamentally different now?
That's a really sharp question because, yes, the physical shrinking, cramming more transistors into the same tiny space, that has definitely slowed down. But the innovation, it hasn't stopped. Not at all. These new approaches, like you said, SoCs, they let us put whole systems, specialized bits, all onto one chip. So you're still getting massive capability increases, even if the transistor count itself isn't doubling quite like clockwork. The innovation just changed form, you could say. It evolved. And look, if the pace in semiconductors felt fast, phew, the jump in AI performance just takes your breath away. Some estimates are saying AI performance on really complex stuff might be doubling every, 3 to 7 months? And the compute needed to train the big models, apparently growing like 4 or 5 times per year, which, leads straight to the big question, how long can that possibly last? When we try to break down why modern AI is so successful, it's not just one thing. Researchers like Leopold Aschenbrenner, Jakob Nielsen, they often point to 3 main pillars working together. First, there's just the raw increase in compute power. Second, big improvements in the algorithms themselves. And third, feeding these systems just vast amounts of data.
Okay, let's dive into that raw compute power. We're talking FLOPS, right? Floating point operations per second on CPUs, GPUs, those specialized AI chips. But you also mentioned effective compute. That sounds crucial. It's not just the raw horsepower, but how efficiently you use it, like getting actual AI results out of those GPU cycles.
Exactly. It's about utilization efficiency. Clever software, doing things in parallel, new ways of designing the AI models themselves, all translating raw power into real performance leaps. And then, pillar 2, the algorithms. This is where you see that almost unbelievable jump. Think about it. 2019, AI could barely string a coherent sentence together. Fast forward to 2023, and some models are passing exams designed for 18-year-olds. Now, comparing AI intelligence to human ages is, it gets simplistic. It's not conscious or anything, but it powerfully shows the rate of progress on certain cognitive tasks, even if general intelligence, real human-like understanding, is still a whole different ballgame.
Right.
So beyond those technical pillars, compute, algorithms, data, there's another huge factor, isn't there? Just the sheer scale of investment, money, and people. We're talking hundreds of billions being poured in by governments, by every big tech company. Everyone wants a piece of this action. And it's not just money, it's human talent too. Seems like almost everyone in computing wants to work on AI now. It's no wonder the pace is picking up with that kind of combined push.
Absolutely. A global, concentrated effort like we've probably never seen before in tech. And we're also seeing this really fascinating convergence happening. AI isn't just, making pictures or writing text anymore. Now AI systems are helping design other complex things, optimizing chip layouts, finding new drug candidates, even designing better AI models. It's like a self-improvement loop kicking in. But, and this is the big but, all of this just circles us back to that critical question you asked earlier. Is any of this truly sustainable?
Yeah, that's the elephant in the room, isn't it? When you see a trend line going up and up and up, it's so tempting to just draw that line continuing forever. But history is littered with examples where that didn't happen. Whether it's stock market bubbles like the South Sea bubble way back when, or, the 2008 financial crisis, winning streaks don't last forever. These historical examples, they kind of teach us to look for the weak points, the unsustainable bits.
Exactly. So applying that lens to computing power and AI, what parts of this incredible growth spurt might be built on shaky ground? We really need to look hard at the fundamentals. Things like physical resources, energy, water, and of course, data.
Okay, let's start with resources, the actual hardware. These AI chips, they need microchips, and microchips are made with rare earth elements.
Right. And what's often glossed over, I think, is how we get those elements, the extraction methods.
Yeah.
They can be pretty damaging to the environment. We're talking significant soil erosion, higher levels of pollutants affecting communities near the mines. It's a hidden environmental cost baked into the hardware.
Okay. That's one pressure point. Then there's energy. We hear a lot about the energy consumption of AI. Companies investing heavily are seeing their energy use soar.
Oh, significantly. Look at the numbers. Google's carbon emissions reportedly went up, 48% in 5 years, largely due to AI in their data centers. Microsoft, something like a 30% increase in 4 years. And think about this comparison. A single query on something like ChatGPT uses roughly 10 times the energy of a standard Google search, a non-AI search.
10 times. Wow.
Yeah. And while, sure, people are working hard on making things more power efficient, there's a catch. It's likely that any efficiency gains won't just mean less energy used overall. They'll probably just enable us to run more AI tasks, maybe more complex ones. So the total demand keeps rising. It's not just about the electricity bill. It really points to a fundamental scalability problem if AI becomes truly ubiquitous. Maybe we need to rethink the core design, not just tweak efficiency.
And producing all that energy, especially for cooling these massive data centers, that requires water. Huge amounts of water. I read somewhere data centers need about 2 liters of water for every kilowatt hour of energy they burn through.
That's the ballpark figure, yeah.
Yeah.
The demand is just climbing as more and more of these huge AI data centers get built. Some estimates suggest AI data centers globally might be using something like 6 times the total water consumption of Denmark, the entire country.
6 times Denmark's water usage. That's genuinely staggering.
It is. It really forces you to confront the geopolitical and environmental side effects of our digital world expanding so fast. You have to ask serious questions about global water security.
Okay, so resources, energy, water. What's the 4th pillar of potential unsustainability? Data. AI models are famously data hungry. They need massive training data sets, especially high quality ones.
Exactly. And some AI researchers are actually starting to see a potential bottleneck here, a data scarcity. There are forecasts suggesting we might run out of high-quality training data, stuff like well-written text and curated images, maybe as soon as 2026. And even lower-quality data, basically scraping the entire internet, might run out sometime between 2030 and 2060.
Run out of data? How?
Well, it's mainly because the models just keep getting bigger and more complex, especially for language. They need more and more unique information to learn effectively. It really begs the question, what happens when these incredibly hungry systems have basically consumed all the existing human-generated information? Where does the new learning come from? So yeah, when you put it all together, there's some really significant challenges on the horizon, more than a few tough problems we need to solve. But, rather than just throwing up our hands and becoming like an AI doomsday prepper, maybe focusing our energy on preventing a potential collapse, finding solutions is a better way forward.
That makes sense. So wrapping this up, what does all this mean for you listening? Well, while it's easy to get caught up in the hype and assume computers and AI will just keep getting exponentially faster forever, maybe that's not guaranteed. History shows us things change. Empires fall, civilizations vanish, species go extinct. These exponential curves, whether in tech or finance, they rarely just go up forever without hitting limits or corrections.
But the old saying holds true. Necessity is the mother of invention. Maybe these very constraints, resources, energy, water, data, maybe they'll force us to innovate in smarter ways, to learn how to achieve more with less, and perhaps most importantly, to get into the habit of asking, before we build the next giant model or deploy the next big system, is this actually a good idea, and what's the true cost?
A really powerful thought to leave people with, especially as we all try to navigate this world being reshaped so quickly by technology and by its limitations. What's the one thing that really stands out to you from this deep dive? Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.